Hey there. Tonight we're sinking deep into the earth, not in a frantic lava-dodging way, but in the slow, sleepy pulse of stone. Beneath your bed, beneath your floor, beneath every clattering street light and forgotten pair of flip-flops, the planet is quietly making more planet. It's a place of melting, cooling, and endless rearranging, an orchestra of elements humming so softly you could miss it if you weren't half asleep already. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, tell me where you're listening from, your city, your local time, because somewhere across the world, someone else is probably dozing off to the same sleepy science. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You start with the ground beneath you, because that's the Earth's first whisper. It's not still. It only pretends to be. Down there, rocks cool and harden their molten ancestors, swirling like thick soup in a cosmic slow cooker. The crust seems thin, fragile, even only about as thick as the shell of an apple, if Earth were the fruit. Beneath it, the mantle moves like cold honey. Iron, magnesium, silicon. On all the quiet stars of geochemistry drift and mingle, trying to find peace in balance. The rocks you stand on, they're survivors of fire. Igneous rocks, the geochemist's bedtime story, are born when magma loses its temper and cools. Basalt, granite, obsidian. All calm versions of chaos, frozen mid-tantrum. Some of them formed under mountains that don't exist anymore. Others flowed from volcanoes that once screamed fire into the air. Yet here they are, silent and unbothered under your feet, supporting your entire existence without ever asking for thanks. Every crystal inside them is a memory. The atoms, oxygen, silicon, aluminum, arrange themselves like disciplined dancers, forming shapes you'd recognize even if you'd never studied geology. Quartz grows in six-sided calmness, feldspar twinkles pink, and mica slices thin enough to almost disappear. You could stare into a grain of granite and see time solidified, a frozen conversation between heat and patience. You might think of the Earth as this messy ball of dirt, but it's a chemist's dream laboratory. Reactions bubble away down there with no deadlines, no anxious postdocs, no safety goggles. Just pressure, temperature, and time, lots of time. The deeper you go, the weirder it gets. At the boundary where crust meets mantle, minerals mutate. They squeeze tighter. They change names like actors switching costumes mid-play. Scientists still argue whether the lower mantle behaves more like a crystal lattice or a sluggish ocean of ions. But either way, it hums with steady confidence. Imagine tracing a single atom of iron. Right now, it might be sitting quietly in a grain of olivine under the Pacific. A few million years from now, that same atom might have melted into magma, erupted, cooled, weathered into sand, and drifted across an ocean. Geochemistry is basically reincarnation for atoms' eternal recycling, with slightly different outfits. And if you listen closely, well, metaphorically, because the decibel level of deep Earth chemistry is zero, you'd almost hear the slow ticking of radioactive decay. Uranium, thorium, potassium, they're the Earth's internal clock and heater all at once. Their decay releases warmth, keeping the core molten and magnetic. Without it, our planet would have gone cold long ago. You wouldn't have volcanoes, plate tectonics, or that mysterious tendency for your phone's compass to point somewhere logical. Speaking of molten hearts, there's a comforting thought. The outer core is mostly liquid iron, swirling around a solid inner core that spins like a stubborn disco ball. This dance creates the magnetic field that shields us from solar radiation. So the next time you use a compass or marvel at the aurora, thank the geochemistry of iron under impossible pressure. It's working overtime unpaid to keep you alive. Here's the fun part, that the rocks don't stay put. Over billions of years, continents drift, collide, and split again, like slow-motion continents practicing social distancing. Ocean crust dives back into the mantle to be melted and reborn. Every mountain chain is temporary, a brief wrinkle in the skin of the planet. The Himalayas, the Rockies, the Alps, they're all just geological hiccups. Blink in geologic time, and they'll be gone. Sometimes geochemists find pockets of minerals that shouldn't exist where they do. Tiny mysteries in otherwise logical rocks. Diamonds, for example, are time travelers. They form deep below in crushing darkness, then hitch a ride upward in volcanic eruptions so fast they don't have time to melt. You might be wearing one on your finger right now, a piece of carbon older than the continents. If that's not romance, I don't know what is. Of course, not everything about the Earth's chemistry is calm. When tectonic plates rub shoulders, friction builds up, an awkward handshake that ends in earthquakes. When magma rises, gases trapped within it expand violently. The chemistry becomes volatile, almost alive. You could call it planetary mood swings if you like. And yet, despite all the heat noise and pressure, the outcome is balance. The crust holds itself together in this improbable equilibrium between melting and cooling, rising and sinking. You can walk across a basalt plain, touch a granite boulder, and never feel the chaos that birthed them. That's geochemistry's greatest trick. It hides its drama under the illusion of stillness. Here's a little secret. Even the ground under your pillow is moving. Not enough to bother you, but enough to matter. The atoms inside the minerals vibrate continuously, exchanging energy like tiny Morse code taps. Those vibrations, called phonons, help conduct heat upward from the planet's belly to its crust. If you could somehow slow down time, you'd see the entire Earth shimmering faintly, pulsing with warmth. It's not dead rock, it's sleeping rock. And maybe that's why you can drift off to it. Because while you sleep, the planet keeps working, mixing, melting, rearranging, recycling. The same chemistry that built mountains now builds dreams. The atoms don't care who's awake, they just keep dancing. Somewhere deep below, molten minerals are cooling into calm, glimmering solids again, ready to tell this story to the next curious mind who presses an ear to the ground and wonders what hums beneath. You drift downward through time, gliding past layers of stone like soft blankets folded over each other. Every layer has its color, its temperature, its mood. The surface where you walk and drop your coffee looks dull and brown, but zoom in and the world explodes into color. Iron stains the earth with rusty reds. Copper adds a blush of green, and manganese hides in quiet purples that only sparkle when you tilt them toward the light. The crust is the planet's painting, an accidental masterpiece, made not with brushes, but with chemistry. Every hue is a signal, a tiny code whispering where it came from. Red desert sands, that's iron oxide, the same stuff that makes Mars look like it's been left in the oven too long. Blue-green streaks in a cliff face, that's copper reacting with oxygen, turning into malachite or azurite minerals, so vivid, ancient painters ground them into pigments. You can still see them glowing faintly in the cracks of old cathedrals. You lean closer, and the texture of a rock tells you its temperature history. Coarse crystals mean the magma cooled slowly, giving atoms time to form neat geometric families. Fine-grained rocks are impatient. They cooled fast, solidified, before anyone could say, "Wait, where does this silicon go?" Scientists still argue whether texture alone can reveal the full story of a rock's cooling, but you can feel that time signature in your palm. If you've ever wondered why Earth's crust isn't the same dull shade all over, think geochemistry's obsession with variety. The planet's crust keeps remixing itself like a DJ who can't stop layering beats iron, carbon, silicon, aluminum, potassium, all shuffling into new combinations. You might say it's the ultimate slow jam. Even the dull gray beneath your feet hides secrets of color. Granite sparkles with flecks of quartz and feldspar. Gabbro gleams dark as midnight with pyroxene and olivine. And basalt, Earth's most common rock, is the quiet black background against which all the colorful chemistry pops. Without it, you'd never notice the blues of lapis lazuli or the orange warmth of jasper. Lapis lazuli, that ancient blue dream, was once worth more than gold. It formed deep in metamorphic zones where limestone kissed magma and decided to reinvent itself. People crushed it into ultramarine pigment for Renaissance paintings, though few knew they were painting with a piece of the Himalayas. There's a kind of poetry in that mountains reborn as sky. And then there's opal. Silica gel that cooled too quickly, trapping water inside. It diffracts light in millions of tiny ways, creating colors that don't even exist in paint. When you look at an opal, you're seeing the spectrum fracture into emotion. Every shimmer, every flicker is a photon bouncing off atomic order. A fun thought: color in rocks is basically a misunderstanding between light and electrons. Different atoms absorb and reflect specific wavelengths. Iron loves to keep the reds, copper prefers greens, titanium likes to show off blues. When light hits a mineral, electrons get excited, literally, and jump between energy levels, releasing photons of certain colors. So when you admire a crystal, you're witnessing a microscopic laser show that's been running for millions of years without an audience. You pick up a pebble from the stream. It looks plain at first, but wet surfaces reveal its chemistry. Silica turns glossy, feldspar shines pink, and little iron nodules glow orange. Water acts like nature's polish, washing away dullness. The same chemistry that oxidizes your car is what makes desert cliffs glow red at sunset. Rust, it turns out, has an artistic side. And then there are the black sands of Hawaii, glistening under the moon. They're made of shattered basalt, cooled so fast it forgot to crystallize. Some grains even contain tiny iron particles that align with Earth's magnetic field. Geochemists use them like compasses, frozen in time, reading the planet's magnetic history grain by grain. That's right, your beach vacation might have been lying on a world-scale archive. There's a strange comfort in knowing that color is evidence of reaction. The planet's surface is constantly experimenting, oxidizing, reducing, blending. Rain pulls ions out of rocks, rivers carry them to the sea, and there they mix again into new hues. Without this chemistry, Earth would be geologically mute, just a silent gray ball floating in space. Instead, we live on a kaleidoscope that's quietly self-repainting. Here's your quirky tidbit for the night: scientists once found a bacteria that actually paints rocks from the inside out. These microbes manipulate iron and manganese to create mineral coatings, turning dull surfaces into metallic rainbows. They've been doing this long before humans thought of graffiti. Life, it seems, enjoys a little art project too. And while some rocks dazzle with color, others prefer mystery. Take obsidian, the volcanic glass so dark it absorbs almost all light, Slice it thin, though, and faint rainbows shimmer beneath the surface. That's caused by microscopic layering during cooling, proof that even darkness has structure if you look close enough. You walk further into the Earth's memory. The palette shifts from surface reds to deep greens and purples. Garnet, peridot, tourmaline. All proof that chemistry can be both precise and indulgent. Each one a different answer to the same question: what happens when elements relax under heat and time? And somewhere down there, buried in stillness, is a crystal that's been glowing faintly for 2 billion years. Zircon. It holds uranium atoms that slowly decay into lead, keeping perfect track of the passage of time. When scientists want to know Earth's age, they ask zircon. It's the planet's personal calendar, and it never forgets a date. You brush the imaginary dust from your hands and breathe in the slow mineral perfume of the planet. Every color you've seen, every shimmer you've traced, it's all the result of atoms deciding who to bond with. Love stories written in silica and iron. Some stable, some fleeting, all timeless. The crust's colors aren't random. They're the visual heartbeat of the world. You just have to slow down enough to see them. And as you sink deeper into that spectrum, you start to feel it, the pulse of stone under your own. The calm rhythm of chemistry, color, and sleep. You breathe in and imagine what it means for a rock to breathe back. It sounds absurd at first. Rocks don't have lungs after all. But in the patient rhythm of geochemistry, even stone exhales. Beneath the quiet crust, gases shift and drift through pores, cracks, and mineral lattices. Oxygen meets carbon, hydrogen meets sulfur, and invisible vapors flow like whispers through the world's oldest plumbing system. You picture it deep under mountains, minerals reacting with rainwater that trickles down through invisible veins. The water dissolves carbon dioxide from the air, becoming slightly acidic. And when it reaches a mineral like feldspar, it starts a gentle chemical conversation. The rock responds, changing form, releasing ions, calcium, sodium, potassium, that flow back upward into rivers and oceans. That's rock breathing. Not in seconds or minutes, but over centuries, like a sleeping creature taking one impossibly slow inhale. This is how the planet keeps its atmosphere stable. Without weathering, carbon dioxide would pile up endlessly, and we'd all be living in a sauna. Every time a mountain face crumbles, it's Earth's version of an exhale trading CO2 from the sky for calcium carbonate in the sea. Later, that carbon gets buried in limestone or chalk tucked away until the next tectonic shift exhumes it again. A billion-year breathing cycle, no chest required. It's strange to think that the Himalayas, those titanic peaks that look frozen forever, are actually part of the carbon cycle's lung. As they erode, they help scrub the atmosphere clean. That's right, mountains are basically environmental air purifiers. Scientists still argue whether uplift or weathering has the stronger hand in regulating global CO2. But it's clear that both are part of the same deep rhythm. And here's a thought to make your pillow feel extra safe tonight. Every breath you take likely contains molecules that were once trapped in a rock, maybe exhaled by limestone in a distant canyon, maybe released from a mid-ocean ridge when basalt met seawater and sizzled. You're recycling Earth's size without even realizing it. You drift further down where the gases grow hotter, the pressure thicker. There's hydrogen bubbling from serpentinized rocks minerals that form when water meets ultramafic crust deep under the ocean. The reaction releases heat and creates methane, a greenhouse gas, yes, but also a feast for microbes that live with no sunlight. These little life forms breathe rock fumes for dinner. They're the planet's original chemists, thriving where no oxygen dares to go. Imagine that life sustained not by photosynthesis, but by geochemical respiration. It's the same logic your lungs use, just slower, stranger, and older than sunlight itself. You realize that maybe the Earth learned how to breathe long before anything with lungs appeared. One of the most delicate exchanges happens along the sea floor, where hydrothermal vents puff mineral-rich plumes into the dark. Iron, sulfur, and carbon swirl like steam from a sleeping dragon. As they cool, they precipitate out into towering chimneys made of metal sulfides. You could call them Earth's exhaled lungs turned to stone. If you could listen, you'd hear a soft hissing, each bubble of gas marking another breath of the planet. Sometimes entire caves act like lungs. Air moves in and out with temperature changes, whispering softly through stalactites. Geologists call it cave breathing, and you can actually feel the airflow if you stand in the right spot. It's like the Earth leaning close to tell you a secret. Of course, not every breath is so gentle. When magma rises, gases dissolved within it. Water vapor, carbon dioxide, sulfur dioxide expand violently. That's what makes volcanic eruptions so explosive. The planet's chest heaves, and the result is thunder, lightning, and rivers of lava. It's dramatic, sure, but necessary. Without those violent exhalations, we wouldn't have an atmosphere rich in carbon or nitrogen. You owe every sunrise to a volcanic belch or two. Even the quietest stones participate. Take serpentine, a silky green mineral named after snakes. It forms where ocean crust interacts with mantle rock and releases hydrogen in the process. That hydrogen can then react with carbon dioxide to make methane. Some scientists think these reactions may have sparked the earliest forms of metabolism, the first breaths of chemical life. Others argue it's coincidence. But either way, the idea that breathing could start without lungs is strangely comforting. Here's your quirky fact for tonight. In certain caves in Italy, rocks literally huff carbon dioxide at measurable rates. Geochemists have nicknamed them snoring stones. These places have been worshipped since Roman times. People thought they were entrances to the underworld. Turns out they were just natural vents from volcanic activity, releasing the planet's sleepy sighs. Everywhere you look, gas is part of the Earth's secret conversation. It seeps from hot springs, fizzes from riverbeds, leaks from the crust, and drifts upward into clouds. Each molecule carries a signature, a chemical passport stamped with its origin. Is it from magma, from limestone? From organic decay, geochemists can tell just by sniffing the isotopes, carbon-12, carbon-13, carbon-14, each one a different note in the melody of respiration. You imagine lying on the forest floor, feeling that invisible exhale rise through the soil. Carbon dioxide flows out, oxygen seeps in, all part of the same planetary rhythm that keeps oceans neutral and skies blue. The air tastes faintly metallic, if you could notice it, a hint of iron and clay. The ground beneath you is not passive. It's exhaling slowly, gently, endlessly. And somewhere in that exchange, your own breathing falls into sync. Inhale oxygen born from rock weathering. Exhale carbon that will one day dissolve into stone. You're part of the same chemistry. You always were. The rock under your pillow might not move tonight, but its atoms are humming, reacting, swapping partners with the air. You and the stone are breathing together, slowly, evenly, peacefully. You sink lower past the rumbling crust and into the realm where minerals begin to sweat. Down here it's warm, not fiery, not molten, but cozy like the inside of a slow oven that's been on since before the moon was born. Water moves through cracks in the rock, invisible rivers carrying secrets. You wouldn't even call it water anymore. It's more like liquid ghost trapped in crystal lattices, hiding in places where no droplet should exist. You reach out in your imagination and touch a grain of olivine. It looks dry, but inside its green sparkle are molecules of H2O water bound tighter than any human handshake. Every crystal down here is a little sponge hoarding hydrogen and oxygen in atomic prisons. If you could squeeze the entire mantle, you might release oceans billions of cubic kilometers of them, enough to drown the continents several times over. And scientists still argue whether that hidden ocean is real, or if it's just a geochemical mirage whispered by deep seismic echoes. The minerals that hoard this water are called hydrous silicates, wadsleyite, ringwoodite, amphibole. You probably haven't met them personally, but they're Earth's best hoarders. Ringwoodite in particular can hold up to 1% of its weight in water, and there's evidence of it existing deep beneath our feet, roughly 660 kilometers down. That doesn't sound like much, but when your rock stretches across the entire planet, it's enough to turn solid stone into a global humidifier. You imagine what that hidden ocean must sound like. A distant heartbeat muffled under layers of pressure. Each molecule trembles in silence, waiting millions of years for a tectonic shift to set it free. When slabs of ocean crust plunge into the mantle, they carry down their moisture, a process known as subduction. Later, when that water escapes through volcanic eruptions, it returns to the sky as steam to fall as rain again. The hydrologic cycle, Earth's infinite recycling loop, doesn't end at clouds and rivers. It dives all the way to the planet's bones. The idea that water hides inside rock feels comforting, like the planet keeps a secret stash just in case. Life depends on this deep hydration more than it realizes. Without water in the mantle, magma would be stickier, volcanoes would be angrier, and plate tectonics might not even exist. The world would be one rigid, unbroken crust, beautiful from space, utterly dead up close. And if you listen carefully to the chemistry, it's poetic. When hydrogen and oxygen meet silicon and magnesium at high pressure, they form minerals that can hold their own against a furnace. It's like water learned how to disguise itself as stone, a liquid pretending to be solid just to stay close to home. You drift through a cross-section of the planet in your mind. The ocean at the surface gleams blue sunlight rippling across it. Below that, the seafloor bends, descends, and carries its soaked sediments downward. Clay minerals transform into denser forms, squeezing out trapped water, which escapes upward through fractures. Each bubble rises like a lost thought. It reaches the surface as steam and joins a cloud that one day rains on your rooftop. You could be drinking ancient mantle tears without realizing it. Here's a fun bedtime fact. Some scientists call this hidden cycle the deep water factory. Every few million years, oceanic plates are consumed, baked and wrung dry like towels. But not all water escapes, some stays locked away. That's why geochemists still debate whether Earth's total water supply has stayed constant for billions of years or if we're slowly leaking it into space. One camp argues that the planet's mantle still holds enough to refill all our seas. Another claims volcanic degassing has been slowly bleeding it away. The truth, probably somewhere in between. Like most of geology, it's less about absolutes and more about balance. There's another trick water performs inside. Rocket makes the impossible happen. When water sneaks into minerals, it lowers their melting point, meaning they can melt at lower temperatures. That's why volcanic arcs like the Andes or Japan exist, where ocean crust dives below continents. Water from the subducting slab escapes upward, turning solid mantle rock into melt. So technically, without that hidden water, you wouldn't have volcanoes, islands, or even the crust beneath your bed. And here's your quirky tidbit for the night. A diamond found deep beneath Brazil once trapped a microscopic pocket of ringwoodite containing water. Scientists used lasers to confirm it. That tiny inclusion, smaller than a grain of sand, was the first direct evidence that the mantle holds oceans' worth of water. Imagine that an entire sea hidden in a gemstone. Nature's version of a message in a bottle. If you could shrink yourself down to atomic scale, you'd see this invisible ocean glittering everywhere. H2O vibrating in slow motion, hydrogen atoms hopping through crystal cages, oxygen forming brief alliances before drifting apart again. It's chaos, but the peaceful kind. No waves, no tides, just endless patient movement. And when that hidden water finally escapes, a volcanic eruption, a geyser, a hydrothermal vent, it carries the memory of its journey. Each droplet has traveled hundreds of kilometers upward through heat and darkness, gathering trace elements along the way. By the time it reaches daylight, it's not just water anymore. It's a story written in isotopes, whispered in steam. You realize that even the rain outside your window tonight might be ancient-born long before trees recycled through the deep earth, more times than you can count. Every glass of water, every wave that laps the shore once passed through a mineral lattice somewhere below your feet. You're not just drinking from the ocean. You're sipping the memory of mountains, the sigh of magma, the pulse of stone. So as you drift deeper into rest, you can imagine that ocean under the crust, glimmering in the dark. You'll never see it, never swim in it, but it's there, quiet, faithful, infinite. The planet's hidden heart, gently keeping time as you fall asleep. You rise toward a gentler realm now, where the sharp edges of mountains slowly turn to dust. Here, time isn't measured in hours or even centuries. It's counted in grains of sand slipping quietly between your fingers. Each one of those tiny grains is a geochemical biography, the last breath of an ancient rock that once towered over the world. Picture it. A granite peak stands proud under an ancient sun battered by wind and rain for millions of years. The temperature rises, the night cools, the rock expands and contracts until hairline fractures spider through it. Water seeps in, freezes, thaws, repeats. Bit by bit, it crumbles. Eventually, gravity wins and the fragments tumble down the slope. The mighty mountain has begun its journey to the beach. That's the secret of sand. It isn't just dirt. It's history in granular form. Quartz, the most stubborn of minerals, survives when everything else breaks down. Feldspar, mica, and amphibole dissolve away, leaving behind the hard, clear skeletons of what used to be continents. If you scoop up a handful of sand, you're holding the ashes of granite, the ghosts of mountains, and the building blocks of future cliffs all at once. When rivers carry those particles to the sea, each grain is sorted like a lazy conveyor belt. The heavier minerals, magnetite, zircon, garnet, settle first. The lighter ones float farther out, sometimes traveling thousands of miles before they finally rest. The beaches you walk barefoot across aren't random. They're chemical sorting stations shaped by density, current, and time. Scientists still argue whether the ratio of quartz to feldspar in modern sand can tell us how fast mountains erode. Some claim it's a perfect clock, others say it's just messy luck. Either way, those tiny grains are timepieces ticking in silence. You pick one up in your imagination and bring it close to your eye. Under magnification, it gleams like glass, scratched and pitted from its travels. Some grains are clear, others smoky or rose-tinted. Each hue comes from trace elements, iron, titanium, chromium, that paint the crystal with faint color. And if you find a zircon grain, congratulations, you're holding one of the most indestructible minerals on Earth, older than many stars you see tonight. Zircons have stories trapped inside them, minute inclusions of uranium that decay into lead at a steady pace. Geochemists use that decay like a stopwatch to measure the age of continents. The oldest zircon found so far plucked from Western Australia is about 4.4 billion years old. That's nearly as old as Earth itself. Think about that, a single grain of sand older than the moon, carried downstream by a river like it's nothing special. And yet sand is never truly still. Even when it seems to sleep on a beach, the wind keeps moving it, grain by grain, sculpting dunes that march slowly across deserts. The air hums with static as particles collide, sharing electrons and tiny sparks. The process is silent to us, but to the planet it's a steady murmur, the sound of the crust rearranging itself for comfort. Here's a quirky fact: in some deserts, the dunes can sing. When the sand grains are uniform in size and perfectly dry, they vibrate together when they slide, creating a low, eerie hum that can last for minutes. Marco Polo wrote about it. Modern geophysicists record it. It's the lullaby of geochemistry, a choir of quartz whispering across the dunes. And not all sand is the same. On tropical islands, beaches shimmer white, not from quartz, but from pulverized coral and shells. Some beaches in Hawaii are green, thanks to olivine crystals from volcanic rock. In Iceland, they're black, made from basalt shattered by waves. Each color is a signature proof that erosion is more artist than destroyer. You can follow sand's journey beyond the sea too. When waves bury it and more sediment piles on top, it becomes sandstone rock reborn from its own remains. Over time, minerals like silica or calcite cement the grains together, gluing them into something solid again. What once was a mountain turned to sand now returns as stone. The cycle is complete. This is what geochemists call diagenesis, the transformation of loose sediment into rock. It happens quietly without anyone noticing as groundwater flows between grains and deposits new minerals in the gaps. It's like the earth tucking its sand in for a long, long nap. Scientists still debate exactly how quickly this process happens. Some sandstones form in mere thousands of years, others take millions. But time isn't really the point. What matters is the patience. The slow, gentle chemistry that never hurries, never stops. And somewhere in that slow transformation, beauty hides. Trace minerals fill fractures with delicate veins, calcite, hematite, or even gold. Fossil shells leave imprints holding memories of vanished tides. Sand, it turns out, remembers more than mountains do. You sit quietly picturing a single grain rolling across the sea floor, bumping into its neighbors, settling again. It doesn't complain. It doesn't hurry. It just waits, perhaps, for another wave, another current, another chance to join something greater. That's the lullaby of the planet: erosion, motion, rest. What falls apart is always being rebuilt. What's washed away is never truly gone. Every grain of sand you've ever touched is proof of it, a reminder that endings in geology are just pauses between transformations. You let the last handful slip from your palm, back to the beach, back to time. The grains settle with a faint hiss, like the earth sighing in its sleep. You linger on the shoreline, watching as molten memories awaken far below. The crust trembles with a quiet heartbeat, and somewhere beneath you, liquid stone begins to move. It doesn't rush, it drifts upward with the patience of mountains being born. Down there, the chemistry is plotting again. Volcanoes are not just angry hills with bad tempers, they're nature's slow cookers releasing deep earth ingredients into the open air. Inside their magma chambers, silicon and oxygen dance in slow spirals, deciding how thick or runny the next eruption will be. More silicon, thicker lava, less silicon, thinner and faster. It's basically the difference between honey and hot soup. And when geochemists talk about viscosity, that's really what they mean. Lava's mood swings. As magma cools, underground minerals begin to crystallize one by one, each leaving behind a slightly different chemical soup. Olivine drops out first, then pyroxene amphibole, and finally quartz, each mineral forming like a guest who decides to leave the party early. This slow separation of minerals is called fractional crystallization, and it's one of geology's quiet miracles. From one blob of molten rock, you can get everything from dark basalt to pale granite. You might imagine the magma murmuring to itself, trying to decide which minerals to keep and which to let go. Maybe a little more feldspar tonight. It hums as crystals grow like frost inside the chamber walls. Scientists still argue whether magma chambers are steady reservoirs or chaotic, ever-changing mush zones. Either way, you can think of them as the Earth's glowing thought bubbles, ideas rising through stone. And when that pressure finally overcomes the weight above the planet, exhales in technicolor. Lava fountains, ash plumes, lightning storms born from friction volcanoes look violent, but at heart, they're artists. Every eruption paints new ground, new minerals, new chemistry. You could say volcanoes are the way the Earth daydreams out loud. Here's the mainstream fact, tucked in with most of Earth's atmosphere, owes its existence to volcanoes. Billions of years ago, before photosynthesis or forests, volcanoes released carbon dioxide, nitrogen, and water vapor. The air you're breathing right now, this exact second, once simmered in magma. It's planetary recycling at its most extravagant. And the quirky tidbit, scientists have discovered lava that behaves like glass in thought. Before an eruption, gases and crystal structures interact in complex feedback loops, sometimes pulsing or resonating like signals. Some volcanologists half-jokingly call this the volcano thinking, because the magma seems to anticipate its own explosion. No one fully understands how, but the chemistry occasionally sends rhythmic tremors, tiny seismic hiccups just before the big show. When the eruption comes, chemistry turns to spectacle. Gases escape, lowering pressure, and bubbles expand in the molten rock. Each bubble bursts, throwing shards of lava into the air that freeze mid-flight into volcanic glass obsidian pumice. The air fills with static and lightning cracks through the plume. It's not just fire and smoke, it's ions trading places, electrons zipping across kilometers of sky, the atmosphere briefly turning into a planetary neon sign. As the lava spreads, it begins to cool, whispering back into solidity. You can almost hear the crystals clicking into place. Basalt flows smooth and dark. Andesite stiffens with stubborn wrinkles. Rhyolite freezes into pale domes. Each type of rock carries its own recipe card, a chemical fingerprint that reveals the conditions of its birth. You step carefully on that new crust in your imagination, feeling the faint warmth beneath your feet. Gases still hiss out: sulfur dioxide, carbon monoxide, water, vapor curling upward into a pale blue haze. The smell of sulfur catches your nose, that eggy tang of new air. It's oddly comforting proof that the planet is alive and exhaling. Sometimes volcanoes don't erupt at all. They just breathe softly through fumaroles and hot springs, releasing minerals that crystallize into fragile patterns. Iron oxides stain the rocks red and orange. Sulfur paints them yellow. If you've ever seen those color-splashed landscapes in Iceland or Yellowstone, you've glimpsed chemistry mid-conversation. The water boils the gas bubbles, and beneath it all, electrons rearrange themselves with ancient calm. You pause over a lava field, cooled but not cold. Black glass glints under moonlight, cracked into ropes and ridges. Touch it in your mind. It's still warm, radiating the planet's slow heartbeat. In each fracture, tiny crystals are growing. The basalt may seem inert, but it's quietly weathering, already forming clays that will one day feed plants. Lava becomes soil, becomes forest, becomes air. Every eruption ends with rebirth. And if you look closer, really closer, you'll see microscopic tubes inside the basalt walls. They're traces of bacteria that once lived on the cooling surface, etched like signatures. Life, it seems, can't resist freshly made rock. It colonizes the newborn crust, almost immediately whispering chemistry into biology once again. You smile at that thought, the planet's wildest experiment, creating both destruction and fertility in one motion. Volcanoes may roar, but their purpose is peace, releasing pressure, renewing crust, maintaining balance. As the lava cools to silence, steam curls upward one last time. You exhale with it slowly. Somewhere deep beneath you, another pulse of magma stirs, waiting its turn. The cycle continues, unhurried, eternal, a reminder that even in chaos, chemistry keeps perfect rhythm. You drift further inward now, where the air fades and the weight of the world presses from all directions. Here, the rocks aren't breaking or melting. They're changing, stretching, and sighing under pressure. Welcome to the metamorphic realm, where old stones are quietly reborn without ever leaving the solid state. Imagine layers of shale gray and unremarkable, buried mile after mile below the surface. Heat builds, but not enough to melt. Pressure mounts, squeezing atoms together like polite strangers in an elevator. The minerals start to shift trading partners and rearranging themselves into new alignments. Clay transforms into mica. Mica folds into shimmering sheets, and before long, the dull shale has become slate tighter, smoother, more refined. The rock just learned discipline. That's the essence of metamorphism: change without chaos. No explosions, no melting, no grand exit, just patience. Rocks that undergo this transformation keep their identity, but acquire elegance like granite that's learned yoga. The result depends on how hot, how deep, and how patient the earth feels that day. Take marble, for instance. Once simple limestone made of seashells and coral, it was buried and cooked until its calcium carbonate crystals fused together like sugar in a hot pan. What began as a soft, chalky sea floor became Michelangelo's playground, smooth, cool, luminous. You could almost hear the faint echo of the ocean still locked inside each gleaming vein. Or think of schist, with its glimmering layers of mica that catch the light like tiny mirrors. Every shimmer is a mineral aligned perfectly by pressure, all pointing in the same direction, as if saluting the same invisible force. Scientists still argue whether the alignment happens more from heat or stress, but either way, it's proof that even in silence, rocks can organize themselves beautifully. You can feel the rhythm of it, temperature rising, atoms shuffling, crystals twisting and recrystallizing. The process takes thousands, sometimes millions of years, and yet the rocks don't rush. They yield gracefully, layer by layer, to the Earth's gentle persuasion. Sometimes the transformation is more dramatic. Under extreme pressure, carbon humbles soot, fragile graphite can rearrange into diamond. It's not magic, it's geometry. The atoms lock into a new pattern so tight that nothing can scratch it. What used to smear across paper becomes the hardest substance known to science. That's metamorphism at its most glamorous, patience turning weakness into brilliance. Here's a quirky tidbit. If you could listen closely to metamorphic reactions, you might hear faint pops and clicks. As new minerals form, they expand or contract slightly, creating microfractures. When those close again, they release tiny bursts of sound, imperceptible to human ears, but measurable by sensitive instruments. The planet is literally whispering as it reshapes itself. And not all metamorphism is slow. Sometimes when a meteor slams into the ground or a fault zone grinds during an earthquake, pressure spikes instantly. Rocks respond by forming shock metamorphics, minerals that only exist under brief but insane conditions. One of them, coesite, is quartz's tougher cousin, formed in seconds and stable only under colossal pressure. Finding it in a rock tells geologists that something violent happened there long ago. Still, the majority of metamorphism is tender an embrace rather than an impact. Water seeps in and helps atoms migrate more easily, like a lubricant for transformation. Chemical reactions ripple through the rock, redistributing elements in elegant gradients. Some of the most breathtaking mineral patterns, banded gneiss, garnet speckled schist, are the result of this subtle rearrangement. Garnets deserve their own moment here. Those deep red gemstones often form inside metamorphic rocks, each crystal growing patiently within a matrix of mica and quartz. Their roundness isn't random, it's chemistry seeking balance. Elements like iron and aluminum migrate toward stability, gathering into tidy clusters until they shine like frozen drops of wine. Geologists sometimes use garnet growth rings like tree rings to read the history of a rock's heating and cooling. Each ring records a pulse of the Earth's long exhale. Scientists still debate exactly where the line between metamorphism and melting lies. Is partial melt still metamorphic, or is it the first step toward igneous rebirth? The answer depends on which geologist you ask and how much coffee they've had. But one thing's certain, every rock has its limit, its threshold between transformation and surrender. You imagine lying deep underground, your body made of crystals and clay, listening to slow waves of pressure pass through you. No panic, no fear, just atoms shifting gently into more comfortable positions. Every stress becomes structure. Every fracture becomes pattern. You realize that maybe the planet's stress management plan is better than yours. And here's a softer image to hold on to as you drift layers of marble and quartzite, glowing faintly under the weight of miles of crust, their minerals bending light into halos. It's warm, hushed, serene. The stones don't resist their transformation. They welcome it. They don't ask when it will end. They trust the process. The deeper you go, the more you feel it, and the earth breathing through change, never breaking, always becoming. Every metamorphic rock is proof that endurance can be beautiful. pressure isn't punishment, it's patience given form. And as you let your thoughts settle into that stillness, you can almost hear it again, the faint, crystalline sigh of the world reshaping itself quietly, forever, somewhere deep below your dreams. You rise slowly from the deep, metamorphic dark into the soft shimmer of daylight, where the air smells faintly of rain and dust. The first drop lands on a warm rock, and suddenly the world fills with a fragrance you know, but rarely think about the smell of the earth itself. Petrichor. It's the planet's perfume, and like any good scent, it's the product of chemistry. Tiny molecules called geosmin made by soil-dwelling bacteria mix with plant oils that cling to dry surfaces. When rain hits, the droplets trap air and fling these molecules into the breeze. Your nose, ridiculously sensitive to geosmin, picks it up at concentrations of just a few parts per trillion. It's one of the most powerful smells in nature, a whisper of wet stone and clean beginnings. You close your eyes and breathe deeper. Every inhale feels like a memory, camping trips, cracked sidewalks after a storm, that first rain after weeks of dust. You might call it nostalgia, but it's really geology talking to your nervous system. You're hardwired to notice rain on dirt because it once signaled survival, fresh water, new growth, clean air. There's something almost poetic about how it happens. When lightning strikes during a storm, it splits oxygen and nitrogen in the atmosphere, forming tiny amounts of ozone. That sharp metallic tang you smell before the rain, that's ozone, nature's announcement that the sky is brewing. Then when the rain finally falls, it releases the deeper, earthier petrichor. The air becomes a layered, symphony metal clay sweetness stone. But there's more to this perfume than rain alone. Rocks themselves react with the air, especially when they've been wet and dry again for ages. Iron-bearing minerals rust just slightly, releasing faint scents of metal and soil. Sulfides mingle in trace amounts, adding a mineral tang. If you've ever smelled the air near a hot spring or volcanic vent, you've caught a stronger version of this hydrogen sulfide, the rotten egg signature of life emerging from stone. Scientists still argue which specific reaction dominates the petrichor aroma. Some claim it's geosmin from microbes. Others point to oxidized oils released by certain plants, or even faint hydrogen bonding in the wet soil itself. The truth is likely all of them, a chorus of reactions perfectly balanced to make your brain sigh in recognition. You step through the scene in your mind. The ground is warm and cracked. The first raindrops strike, releasing bursts of earthy fragrance. A breeze carries it toward you, laced with faint traces of clay and ozone. You exhale, and for a moment, you can almost hear the soil sigh back. There's a reason this smell feels calming. It's connected to the oldest exchange between life and earth. Those same bacteria that create geosmin are part of the planet's mineral cycle. They break down organic matter, release nutrients, and leave behind the molecules that perfume the air after rain. Every inhale of petrichor is also a whisper from those ancient chemists beneath your feet. Even space has its version of scent. Astronauts returning from spacewalks have reported that their suits carry the smell of burnt metal or ozone and seared steak. It turns out that atomic oxygen formed in the upper atmosphere and on spacecraft surfaces reacts with the oils and metals on their suits. The smell is cosmic petrichor chemistry reborn in vacuum. It's a reminder that scent is universal atoms expressing themselves through reaction. You wander through the wet landscape, watching the droplets gather on leaves and roll down into the soil. Each drop carries dissolved minerals, calcium, magnesium, potassium, back into the Earth's chemistry lab. When the rainwater soaks deeper, it becomes groundwater, picking up ions along the way. The taste of every spring and well owes its flavor to the minerals it met underground. That hint of sweetness in fresh water, that silica, the metallic tang iron. Even water's transparency is a result of its clean chemistry. It absorbs light so gently that it lets almost everything pass through. Here's your quirky tidbit for tonight. Scientists once recreated petrichor in the lab to help astronauts feel at home. They synthesized geosmin and mixed it with ozonated water to mimic the smell of rain on Earth. Some called it bottled nostalgia, but it worked. Astronauts reported feeling calmer, more grounded. Imagine that Earth's chemistry turned into aromatherapy for space travelers. Rain continues to fall softly in your mind. The air grows cool, the sound steady and slow. You trace the droplets as they seep into the cracks of a rock. Each one triggers micro-reactions, dissolving carbonates, rusting iron, washing away salts. The rock changes molecule by molecule without ever seeming to move. Over centuries, this same process will sculpt landscapes, carve canyons, and paint cliffs with streaks of mineral color. Scientists still debate just how much the planet's scent influences ecosystems. Some think petrichor helps seeds germinate, triggered by the humidity and chemicals in the air. Others suspect animals, especially desert insects, use the smell to track storms. The evidence is thin, but the idea is lovely that somewhere a beetle smells the rain before you do and begins its own tiny migration. You breathe again, slower this time. The scent fades, but leaves a softness behind a kind of clarity that only follows a storm. It's the smell of balance restored, the earth exhaling after a long, dry wait. As you drift deeper into calm, you realize you've been breathing the same chemistry as mountains, microbes, and clouds. The scent of rain on stone isn't just a smell. It's a dialogue, an invisible handshake between life and rock. Somewhere beyond your window, maybe even right now, the sky is preparing another rain. The stones are waiting dry and silent, ready to release their next sigh of petrichor into the air. And when it comes, you'll know. You'll lift your head, close your eyes, and smile without knowing why. The planet is speaking softly through chemistry, and you are listening. You step deeper underground again, where silence echoes and minerals drip like slow clockwork. The air is cool, heavy with humidity, and the walls glisten with faint crystals. Welcome to the caves of Carbon Earth's slowest artists, shaping stone into lace with nothing but water and patience. Here, chemistry moves one drop at a time. Each droplet of groundwater carries a whisper of carbon dioxide absorbed from the soil above. As it trickles through limestone, the gas reacts with calcium carbonate in the rock, dissolving tiny amounts of it into solution. When the drop finally falls from a cave ceiling, it releases that CO2 back into the air, leaving behind a grain of calcite. Then another drop comes, and another. Layer by layer, stalactites and stalagmites grow toward each other, like lovers inching closer through centuries. It's the slowest romance imaginable, but a faithful one. In a good year, a stalactite might grow a few millimeters. That means some of the pillars you see in vast caverns, massive, glittering columns stretching from floor to ceiling, have been forming since before the first humans made fire. You shine your imaginary flashlight upward. The ceiling glows with translucent curtains of stone so thin that light passes through them. Scientists call them draperies. Each ripple marks a shift in drip rate or mineral saturation, essentially a diary entry written by water. You can read the cave's history in the patterns, droughts, floods, even traces of ancient air trapped in calcite layers. Geochemists actually extract these clues analyzing isotopes of oxygen and carbon to reconstruct past climates. The cave, it turns out, is an unbroken timeline of weather written in stone. Scientists still argue whether stalactites grow steadily or in spurts depending on humidity. But all agree that they're geological perfectionists. No rush, no shortcuts. Just chemistry doing yoga at 1 drop per second. If you follow the stream deeper, you'll find flowstones, broad glossy sheets where mineral-rich water glides across sloping walls, spreading calcite in smooth waves. They look like frozen waterfalls, but touch them, and you'd feel warmth from the air moisture life. Yes, life. Because even here, bacteria help shape the stone. Microbes coat surfaces, changing pH levels and guiding crystal growth. So while the cave seems lifeless, it's actually co-authored by biology and geology. And sometimes these collaborations create something stranger. Deep within certain caverns, scientists have found pools of milky water containing floating calcite spheres called cave pearls. Each one forms as drops of water fall into a pool coating a tiny nucleus, a grain of sand, a fragment of bone with layer after layer of mineral. They're smooth, round, and astonishingly beautiful, like nature's forgotten jewelry. Here's your quirky tidbit for the night some stalactites actually sing. When air currents flow through narrow tubes, they vibrate like flutes, producing faint tones. Explorers once thought they were spirits whispering in the dark, but it's just physics and chemistry performing an impromptu concert. So yes, caves literally hum to themselves as they grow. Further along, you pass through chambers filled with aragonite crystals, needle-like and fragile. Unlike calcite, aragonite forms under slightly different conditions, favoring higher CO2 concentrations. It sparkles like frost, delicate yet eternal. The transformation between calcite and aragonite fascinates scientists because it's reversible. Heat or time can turn one into the other, meaning these structures are constantly evolving even when they appear frozen. If you look closely, the cave walls are alive with texture botryoidal formations that resemble bunches of grape soda straws, so thin they could snap from a whisper, and rimstone dams built by mineral-laden streams pooling into terraces. Each form is a record of how carbon interacts with water, rock, and air. Every droplet is a geochemical equation in motion. And while carbon here is gentle, it's the same element that fuels volcanoes, powers life, and builds diamonds. It doesn't pick favorites. It simply cycles through forms eternal and adaptable. Right now, it's busy constructing stone lacework for no audience. But the passing bat and the occasional curious geochemist. In a darker corner, you spot something eerie, a small mound of white crystals glowing faintly under your light. It's moon milk soft, chalky deposits of calcium carbonate mixed with microbial colonies. For centuries, people thought it was magical ointment. In a way, it is a mixture of chemistry and life gentle enough to smear with a fingertip, yet strong enough to harden into stone. You sit beside an underground pool and listen to the plink of water. Each drop echoes like a heartbeat. Time feels stretched, viscous. You realize that in this place, slow isn't a word, it's a philosophy. The planet teaches patience here. No hurry, no deadlines. Just drop, pause, crystallize, repeat. The carbon cycle above ground trees inhaling oceans, dissolving volcanoes venting, feels frantic compared to this serenity. Down here, carbon finds peace. It's content to linger in mineral form, dreaming of someday returning to the air as a sigh of carbon dioxide. You breathe in slowly and imagine that cycle. A molecule of CO2 leaves your lungs, drifts through the air, dissolves in rainwater, slips underground, and eventually becomes a layer of calcite in a cave ceiling. Someday, a curious traveler might stand beneath that formation and wonder how it formed, unaware that your breath helped start it. It's a comforting thought. You too will join the chemistry of the world, not in some distant metaphorical sense, but literally. The carbon in your body, the calcium in your bones, the minerals in your blood, they'll all return to the slow art of geochemistry. You're part of the sculpture already. The last droplet falls into the pool with a soft ripple. The sound fades into the distance, blending with the hum of unseen air currents. You feel the weight of stone above you, steady and eternal. The cave exhales once more, slow and sure. You can almost hear it murmur, "Nothing is wasted, only transformed." You climb gently from the dripping stillness of the caves into the chill of the stars. The ground under you hardens smooth and metallic, as if the planet itself were wearing armor. It gleams faintly in starlight, nickel, iron, cobalt. You reach down and pick up a fragment, a meteorite older than Earth, colder than memory. It's heavy for its size, unnaturally dense, and flecked with metallic sheen. You turn it over and see the intricate crisscross pattern on its surface. The Widmansten pattern, a lattice that only forms when molten iron cools over millions of years in the vacuum of space. No forge on Earth could reproduce it naturally. This isn't just a rock. It's a relic of stellar chemistry, a piece of a long-dead planet that never finished forming. Each meteorite carries the same raw ingredients as you do iron for blood carbon, for life magnesium for bones. You realize as you cradle it that geochemistry doesn't start on Earth. It's universal. Everything here, every grain of sand, every drop of water, every atom in your body, was once part of a cosmic reaction cooked in the heart of a star. You look closer and notice tiny shimmering grains embedded within the metal. Those are chondrules, perfectly round droplets of melted rock frozen in time. Scientists still argue whether they formed from lightning in the early solar nebula or from shock waves of exploding stars. Whatever the truth, they're the oldest solids in the solar system, little marbles of molten dawn. Hold one long enough, and you're holding 4.6 billion years of history. That's not exaggeration. It's laboratory-verified fact. Some meteorites even contain organic molecules, amino acids, sugars, and the chemical seeds of life. The same carbon chains that drifted through space may have rained onto the young Earth, starting the biochemical whispers that eventually led to you listening right now. You roll the meteorite in your palm. It's cold, but not lifeless. Its chemistry is still reacting ever so slightly with Earth's air and moisture forming thin films of rust. The universe, it seems, never stops oxidizing itself. Even a cosmic visitor can't escape the planet's atmosphere joining the conversation. In Antarctica, scientists collect these travelers from the ice, their dark forms easy to spot against the white. Many of them have been there for tens of thousands of years, waiting patiently for human curiosity. They tell stories of asteroids colliding planets, shattering, and space dust clumping together under gravity's quiet spell. Every one of them is a fragment of a failed world, or perhaps a preview of one yet to come. And here's a lovely irony: some of the rarest meteorites come not from asteroids, but from Mars and the Moon, blasted away by impacts and flung through space until Earth's gravity pulled them home. You could hold a piece of another planet in your hand, a rock that saw two skies, two worlds, and billions of miles in between. Scientists still debate how much extraterrestrial material lands on Earth every day. Estimates range from 5 to 300 tons of cosmic dust. That means right now, while you're listening, particles from distant asteroids are settling quietly onto your roof, your garden, maybe even your hair. The boundary between Earth and space is blurrier than it seems. And here's your quirky bedtime fact: a meteorite once crashed through the roof of a house in Alabama in 1954 and hit a woman named Ann Hodges while she was napping on her couch. She survived with a bruise and became the only confirmed human ever struck by a meteorite. The universe apparently has a sense of timing. You imagine the fireball streaking across the sky, the brief flash of ionized air, the hiss as it cools on the ground. The chemistry that shaped entire planets condensed into a single glowing pebble. And then it just lands, quiet again, waiting for someone to notice. If you slice open an iron meteorite, you'll see the pattern again, intersecting lines of kamacite and taenite nickel-iron alloys that separate out as the metal cools impossibly slowly in microgravity. Each line marks thousands of years of peace between heating events, each intersection a pause in the chaos. It's as if the universe itself stopped to rest between explosions. You hold the fragment to your ear, pretending you can hear its origin. Maybe a distant star once collapsed, scattering elements in every direction. Maybe this piece drifted through darkness for eons untouched, until gravity and fate guided it here. Maybe you and this meteorite are cousins, sharing atoms forged in the same stellar furnace. It's comforting to think that geology doesn't end at Earth's edge. Out there on Mars, Venus, and countless moons, similar reactions are happening right now. Iron oxidizes, carbonates form ice, sublimates, crystals grow. The same periodic table writes endless variations of the same melody across the cosmos. You place the meteorite back on the ground. The soil accepts it, quietly folding it into the planet's collection of memories. Rain will rust it, microbes will taste it, and one day it will blend into the crust like it had always been there. Space becomes Earth. Earth becomes space. The difference was only ever a matter of time. You look up at the stars again, realizing they're not distant, they're ingredients. Every twinkle is a chemical promise, a future mineral, a future you. The whole universe is one vast laboratory, and you're breathing its ongoing experiment. The meteorite under your hand cools further, the starlight fading off its surface. Somewhere far away, another one begins its long fall, tracing a line of fire across the night. A cosmic sigh, a shooting star, another sample on its way to join the Earth's grand geochemical dream. You're back on the planet's surface now, walking across a plain so bright it almost stings your eyes. Everything around you sparkles flat fields of salt stretching into the horizon like glass shattered into perfect stillness. The air smells faintly metallic, dry, and crystalline. You're standing in the ghost of an ocean. Long ago, this place was water, not just a puddle or lake, but a vast inland sea shimmering under an ancient sun. Rivers fed it, wind rippled it, and rain returned it again and again. But over time, heat outpaced replenishment. The sea began to evaporate, retreating slowly, leaving its chemistry behind. What remained were salts, halite, gypsum, and hydrite layered like frost on forgotten memories. If you kneel and touch the ground, your fingers pick up tiny cubes of salt-perfect geometric crystals grown naturally under sunlight. Each one is the planet's handwriting, spelling out its long, slow evaporation. What was once fluid became solid. What was once ocean became desert. Salt is more than seasoning, it's memory. When water evaporates, it doesn't just vanish, it transforms. The minerals dissolved within it, sodium, chlorine, calcium, potassium, begin to bond and crystallize in exquisite order. Each layer tells you about the climate of its time temperature, humidity, even atmospheric composition. That's why geochemists love evaporates. They're like climate diaries written by vanished seas. Scientists still debate just how much of Earth's salt comes from volcanic outgassing versus erosion. Some argue that seawater chemistry stabilized billions of years ago. Others claim it's still evolving. What's certain is that every salt crystal you've ever seen is part of an endless chemical rhythm, the ocean breathing in and out across geologic time. You stand on the edge of what used to be the Mediterranean basin, or maybe the ancient Lake Bonneville, or perhaps Bolivia's Salar de Uyuni, the world's largest salt flat. It doesn't really matter. They all tell the same story. As the last of the water evaporated, minerals precipitated in perfect sequence, first carbonates, then gypsum, then halite, then the rarer salts like sylvite and borax. The order never changes. Chemistry loves consistency, even as landscapes shift. The ground beneath you glitters like frost, but this frost never melts. During the day, sunlight bounces off every facet, blindingly white. At night, under moonlight, it glows silver blue. Travelers once mistook the Salar de Uyuni for a frozen lake, only to discover it was dry as bone. When it rains just a little, though a thin film of water spreads across the flats, turning them into the world's largest mirror, sky and earth become indistinguishable. And for a brief moment, the planet reflects itself perfectly. That mirror effect is a quiet miracle of chemistry. The salt layer is so smooth that the shallow water forms a flawless reflective surface. Each sodium chloride crystal dissolves slightly, creating just enough tension to even out the ripples. It's molecular teamwork at its most aesthetic. You reach down again and taste a grain. It's sharp, clean, familiar. The same sodium chloride that seasons your dinner table. The same compound that flows through your blood, helping neurons fire and muscles contract. Salt connects your body to the planet. You carry miniature oceans within you, electrically charged reminders of the sea that raised your ancestors. Here's your quirky tidbit for the night deep underground. There are entire salt glaciers, slowly flowing like syrup. They form when buried halite layers deform under pressure, squeezing upward into dome-shaped structures that can pierce through miles of rock. In some places, these salt domes trap oil and natural gas, turning ancient chemistry into modern industry. The Earth is still sculpting itself with the leftovers of vanished seas. You wander further into the salt plain. Small pockets of life persist here, halophilic bacteria and algae that thrive in salinities that would kill almost anything else. They tint the crust pink and orange, painting life's stubborn persistence across the harshest canvas. The same kinds of microbes may exist on Mars today, hidden in briny pockets beneath the surface. The colors you see here could be a rehearsal for alien sunsets. The air trembles slightly in the heat, and you notice patterns etched into the crust, hexagonal polygons stretching as far as the eye can see. They form as the salt dries and contracts, cracking along precise geometric lines. It's nature's tessellation, no artist required. You can almost hear the faint crunch beneath your footsteps, each step producing a tiny spark of sound like breaking glass. Scientists study these polygons, not just for beauty, but for what they say about water's retreat. The shapes record humidity cycles, temperature shifts, even wind direction. Some of the oldest preserved salt flats on Earth hold these patterns from millions of years ago, unchanged, their geometry still crisp as origami. You think of how fragile the whole scene is. A single rainfall could dissolve the surface, reshaping it entirely. And yet, that fragility is what makes it eternal, the constant cycle of destruction and recreation. In geochemistry, impermanence is just another kind of stability. The light begins to fade, and the salt turns from white to gold, to rose to violet, mirroring the sky's own gradient. You feel like you're walking on light itself. Beneath your feet, trace amounts of trapped air hiss softly, ancient bubbles finally escaping. It's as if the old ocean is whispering its final goodnight. You close your eyes and listen. The world smells faintly sweet from evaporated gypsum. The wind hums across the flat expanse, and the air tastes of salt and silence. Everything's still, everything's simple. The chemistry here is pure, unpretentious. Just water leaving minerals, staying the planet, balancing its books. Somewhere deep below, the same process continues in miniature, tiny brine pools, slowly crystallizing, storing the story of today's climate for future geologists to read. The salt beneath you isn't static. It's writing. And with every breath, you contribute a molecule or two of water vapor to the air atoms that might one day fall here as rain and start the cycle again. You walk until the horizon blurs the stars, reflecting both above and below. The line between sky and ground vanishes, and you float surrounded by infinity made of salt and starlight. The world exhales calm and crystalline. You leave the brightness of the salt flats and wander into a world of softness, the realm of clays. The ground beneath you darkens, cools, and turns velvety. When you step, it gives slightly like memory foam made by the planet itself. Every footprint holds shape for a moment before slowly relaxing, as if the earth has decided to remember you just long enough to be polite. Clay may seem humble dirt, mud, something to wash off, but geochemically, it's one of the most important materials on the planet. It's the great translator between rock and life, the quiet middleman that negotiates between solid and liquid, mineral and organic, past and future. You crouch and run your fingers through it. The grains are impossibly fine, smaller than dust, smaller than light can easily see. Each particle is a sheet of atoms thin as a thought, arranged in layers like pages in a book. These sheets can trap water molecules between them, swelling and shrinking depending on moisture. That's why clay feels so alive. It literally breathes with humidity. If you add water, it turns supple and obedient. If you bake it, it hardens into permanence. That duality, soft and strong, transient and eternal, has made clay humanity's oldest collaborator. Pottery, bricks, tablets, our first attempts at writing, building, and art all began with this unassuming mineral slurry. You could say civilization itself started because clay was willing to listen, but long before humans shaped it, clay was already busy changing the world. It forms when feldspar and other silicate minerals weather, breaking down under the touch of water and carbon dioxide. The reaction rearranges atoms into new configurations, creating minerals like kaolinite, elite, and smectite. Each type holds water and ions differently, making clays the chemical sponges of the planet. In soil, these particles control fertility. They hold nutrients like calcium, potassium, and magnesium, releasing them slowly to roots. Without clay, rain would wash everything valuable away. Plants owe their lushness to these invisible geochemical caretakers, quietly balancing charges underground. Scientists still argue about the exact role clays played in life's origin. Some think early organic molecules, amino acids, nucleotides, assembled on clay surfaces. The sheets provided structure and protection, aligning molecules into patterns that could replicate. Others argue that volcanic vents did the job instead. But many agree that clay may have been the first stage for biology's grand performance, the world's original Petri dish. You smile at the thought of life rehearsing in mud. The first cells perhaps born not in fire or lightning, but in the gentle grip of damp clay, sheltered from chaos by minerals that preferred order. Here's your quirky fact. Certain clays can actually remember what ions they've met. Through a process called cation exchange, they swap charged atoms with water, recording their past chemistry like diary entries. When geochemists study ancient clays, they can reconstruct which elements were present in the environment millions of years ago. The mud is keeping secrets. You dig deeper with your imaginary hands. The smell changes, earthy, metallic, faintly sweet. That's iron and organic matter, mingling the scent of living soil. Under a microscope, you'd see miniature landscapes of flakes and channels, water moving through them like a lazy stream. In that water are ions, sodium, calcium, magnesium, slipping between layers like guests at an endless cocktail party. Clay also has an aesthetic side. Some varieties like bentonite expand dramatically when wet. Others like kaolin stay smooth and silky, used for fine porcelain. There's even green clay, rich in iron, that spas use for detox masks. Chemistry is skincare. You could say geochemistry occasionally moonlights as a beauty consultant. And clay isn't confined to Earth. On Mars, orbiters have detected extensive clay deposits, proof that liquid water once sculpted the red planet. The presence of these minerals tells scientists that Mars wasn't always dry and barren. It once had the same patient chemistry of water meeting rock, quietly rearranging atoms in peace. If life ever began there, it likely started in Martian mud. The world beneath you shifts as rain begins to fall. Each drop hits the clay, forming tiny ripples. The surface drinks deeply, swelling, darkening. Water molecules slip between atomic sheets, pushing them apart. The ground exhales a soft sigh. When the rain stops, the air fills with that familiar scent, half organic, half mineral, the same perfume that rises from garden soil after a summer storm. You realize clay is nature's memory. Foam for rain it absorbs, holds then releases in slow rhythm. Scientists still debate why clays align into such perfect sheets. Some say it's pressure from burial. Others think electrostatic attraction does the trick. But the result is always the same microscopic order, creating macroscopic calm. You pick up a small piece, roll it between your fingers, and it warms quickly, taking your shape. You could sculpt anything from it, a cup, a tablet, a figure, and it would hold that form as long as you let it. Even fired, it would still contain traces of its origin, the silicon and aluminum lattice, the faint whisper of water it once held. Clay never forgets what it was. There's something deeply comforting about that. You too are made of atoms borrowed from stone and air, rearranged briefly into softness. When you touch clay, It feels familiar because on a molecular level, you're cousins. The planet simply found another way to organize the same ingredients. As you stand again, the world around you feels quiet but awake. The hush after rain, the scent of wet earth, the coolness of shade. Beneath your feet, the clay continues its slow choreography of absorption and release, an unseen pulse that connects everything living to everything that isn't. You take one last deep breath. The air is heavy grounding. You let it fill your lungs and settle your thoughts. Clay doesn't rush, doesn't resist, doesn't cling. It simply adapts. Maybe that's why it feels so peaceful to stand on. You're standing quite literally on the patience of the planet. The ground beneath you begins to shimmer, flecks of metallic yellow catching sunlight through thin layers of quartz and stone. You know that glint instantly. Humans have chased it for millennia. Gold, the planet's most notorious distraction and one of geochemistry's strangest tricks. You kneel beside a creek water gliding over sand and pebbles. A flash appears between ripples, vanishes, and returns. That tiny sparkle might have once changed the course of history. Prospectors, kings, dreamers, they all searched for this color, unaware that it wasn't rare by cosmic standards, only beautifully inconvenient to find. Gold doesn't rust. It doesn't tarnish. It's indifferent to time. That's why it's still here, glittering quietly while everything else crumbles. Chemically, it's one of the most reluctant elements, noble, the scientists say, meaning it refuses to bond easily with others. In a world obsessed with change, gold prefers solitude. But even this aloof metal has a backstory. It was born in violence, in the final heartbeat of dying stars. When neutron stars collide, they forge heavy elements like gold and platinum in mere seconds. Those atoms then scatter across galaxies, eventually coalescing into dust, then planets, then rivers. The gold dust under your fingertips once flashed into existence during a cosmic explosion, powerful enough to reshape space itself. And now here it sits gleaming in a stream, waiting patiently to be noticed. You swirl the sediment in your handpan, letting the lighter sand drift away. The gold flakes sink loyal to gravity. You smile, its chemistry doing simple math density. Gold is nearly 20 times heavier than water, so it resists every attempt to float away. Every nugget found, every coin minted, is the result of water performing this subtle calculation over thousands of years. Geochemists know that gold rarely appears alone. It travels with sulfur-forming compounds like pyrite fools gold. Pyrite's bright brass sheen fooled countless miners, but it's also a vital clue. Gold often hides inside or beside it, bound to sulfur atoms in microscopic veins. Under the right temperature and pressure, those bonds break and true gold precipitates out, leaving a metallic fingerprint that prospectors follow like treasure maps written by the planet. Scientists still argue over the exact mechanism that concentrates gold. Some say hydrothermal fluids, superheated water coursing through fractures, carry it in dissolved form, depositing it as they cool. Others suspect bacteria play a role, their metabolic byproducts, subtly precipitating microscopic gold particles. Yes, even microbes might be tiny alchemists crafting gold dust cell by cell. Here's your quirky tidbit. In Australia, scientists discovered eucalyptus trees that actually mine gold. Their roots penetrate deep enough to reach auriferous soils, absorbing trace particles that accumulate in their leaves. When those leaves fall and decay, they leave microscopic gold behind. Nature, it turns out, invented a low-energy extraction method long before we did. You run your fingers along a quartz vein cutting through the bedrock. Inside, thin threads of gold glimmer like veins of sunlight trapped in stone. They formed when mineral-rich fluids cooled rapidly, locking metal and crystal together. Each thread marks a moment of planetary exhalation, a quick drop in temperature and pressure that froze chemistry mid-thought. Over millions of years, erosion frees these veins, breaking the rock apart and releasing the metal into streams. That's how placer gold forms, collecting in quiet bends and eddies, where water slows enough for heavy particles to rest. You could call them nature's piggy banks, small deposits of cosmic inheritance tucked into riverbeds. It's strange, though. Despite gold's beauty, it serves little biological purpose. Iron carries oxygen and blood, magnesium fuels, chlorophyll, calcium strengthens bones. But gold, it just shines. Maybe that's why humans love it so fiercely. It symbolizes permanence in a world built on decay. It's the geochemical equivalent of silence nothing to fix nothing to fear, just eternal shimmer. And yet, even gold yields to time. In rare conditions, it can dissolve in solutions of chlorine or cyanide, chemistry's reminder that invincibility is an illusion. That's how industrial refining works, by tricking gold into forming temporary chemical bonds it would otherwise reject. You can almost imagine it sighing reluctantly, agreeing to participate. Beneath your imagination's lens, the entire crust glows faintly with traces of metal-iron veins, copper seams, silver threads, platinum sparks. The earth is a tangled tapestry of metallic whispers, all stitched together by hydrothermal chemistry. But gold remains the quietest note, shining softly among the rest, refusing to tarnish or fade. You think about how civilizations built empires chasing this glow. Entire rivers dredged mountains, gutted people, uprooted, all for a metal that, scientifically speaking, does almost nothing. Yet perhaps that's the lesson. Gold doesn't do, it is. In the stillness of its atomic structure lies something we instinctively recognize: peace. You take a deep breath and watch the light fade from the stream. The gold glints once more, then dims as dusk settles. The metal doesn't care whether it's admired or ignored. It's been here for billions of years and will stay long after you're gone. That kind of patience humbles even the stars. As you stand, you brush your hands clean. Tiny flecks of mica catch the last light, fool's gold pretending to matter. But you know better now. The real treasure isn't wealth. It's the quiet persistence of chemistry itself, repeating the same experiments forever, never tired, never bored. Somewhere, a mountain vein is cooling. A quartz pocket is sealing, and a single atom of gold is settling into place. It won't move again for 1,000,000 years. Maybe 2. It doesn't have to. Its content simply to exist, to shine faintly in the dark, reflecting the last glimmers of sunlight through rock and water. That's the true luxury of gold. It reminds you that even in an ever-changing world, some things are allowed to just be. You turn away from the glitter of gold and feel the faint rumble beneath your feet. The earth is stirring again, not with violence, but with rhythm. The ground breathes in slow pulses, entire continents shifting, as though the planet itself were dreaming. You're standing on the pulse of tectonics, the slow heartbeat that keeps everything in motion. It starts invisibly deep, below where molten rock flows like thick syrup. The mantle doesn't boil or churn. It circulates in convection cells, hot material rising, cool material sinking. That movement tugs on the crust, splitting it apart at some places and crushing it together at others. You can't feel it directly, but it's happening right now beneath your toes, a few centimeters per year, as relentless as a ticking clock. You picture the plates like enormous rafts drifting on a molten sea. At their edges, magic or madness happens. When two plates diverge, new crust forms. Magma wells up, cools, and solidifies into basalt, adding fresh skin to the planet. At mid-ocean ridges, this process draws lines of fire across the sea floor, an underwater zipper endlessly unzipping and resealing itself. When plates collide, the story changes. One dives beneath the other in subduction zones, dragging oceanic crust deep into the mantle. As it sinks, the pressure and heat release water melting nearby rock and fueling volcanoes at the surface. The Andes, the Cascades, the Japanese archipelago. They're all born from this dance of destruction and renewal. You could say mountains are wrinkles from the earth, frowning in concentration. Scientists still argue what started plate tectonics in the first place. Did the planet begin with a stagnant crust that fractured as it cooled, or has it always been restless? Some theories suggest early asteroid impacts shattered the surface and jump-started the process. Others propose that radioactive heating from within created enough buoyancy to keep it moving. The debate continues, but the rhythm doesn't wait for an answer. You walk toward a mountain range, rising in the distance, each peak the result of two plates colliding in slow motion. Beneath them, metamorphic rocks grind against one another, quartz veins shear and reform, and faults slip like slow sighs. Every tremor you've ever felt, every earthquake that rattled a window pane, is a whisper of that underground ballet. The chemistry is subtle, but crucial. As rocks descend into the mantle, they react with high pressure and water to release carbon dioxide. That gas travels upward through magma and vents into the atmosphere, completing a planetary loop that balances climate. If tectonics ever stopped, Earth's carbon cycle would freeze. No volcanoes, no fresh minerals, no renewal. The world would turn stagnant, an aging planet holding its breath. You pause for a moment and place your hand on the ground. Somewhere beneath you, deep faults creep a few millimeters per year. Their friction creates heat, their stress builds energy, and when that energy releases, the planet adjusts its posture. Earthquakes aren't punishment. They're stretches, tiny muscle spasms in the crust, keeping the body of the world flexible. In Iceland, you can stand in a rift where the North American and Eurasian plates are slowly pulling apart. The valley widens by a few centimeters each year, invisible but real. Tourists take photos standing with one foot on each continent, grinning unaware they're posing on chemistry in motion, silicates expanding basalt, crystallizing gases, whispering from vents below. Here's your quirky tidbit. There are microplates, smaller fragments of crust that move independently like tiny tectonic side characters. One of them, the Juan de Fuca plate off North America's coast, is responsible for much of the region's volcanic activity. It's small but determined proof that even the tiniest piece of Earth's crust can reshape coastlines given enough time. The more you imagine it, the more the entire planet feels alive. Magma flows beneath ocean ridges like blood through veins. Volcanic arcs flare like nerve signals. Even the magnetic field generated by iron circulating in the outer core pulses in rhythm with tectonic movement. Geochemistry isn't just reaction, it's circulation. The Earth is a body, and the plates are its muscles. You climb a ridge and gaze across a folded valley. The rocks tell their story plainly, once horizontal, now bent like pages in a book pressed too long. Quartz veins shimmer in the creases, evidence of fluids once trapped and released during compression. You can trace fault lines like scars, beautiful functional reminders that healing often leaves texture behind. Scientists still debate how deep the cycle truly goes. Some suspect parts of the lower mantle might also circulate, slowly mixing Earth's interior chemistry over billions of years. That's why the oldest rocks never disappear completely. They just change roles, passing through metamorphism, melting, and crystallization in an endless loop of recycling. The planet's crust in its entirety is a masterpiece of reuse. As you watch clouds drift across the peaks, you realize that everything, the air you breathe, the rain that falls, even the color of the soil, depends on this movement. Without it, continents wouldn't drift, oceans wouldn't renew, and minerals wouldn't mix. Earth would be static, sterile, unchanging. It's tectonics that gives the planet personality. You lie back on the warm stone, feeling faint tremors echo through it. They're too subtle to notice, but you imagine them anyway. The pulse of molten rock rising, the faint shift of fault lines adjusting. The Earth doesn't roar or rage, it simply breathes in billion-year intervals. You exhale with it, your breath sinking to a rhythm you can't see but somehow understand. The sky grows dim, and in the fading light, the mountains look like waves frozen mid-crest. Maybe that's what they really are. Solidified ripples of chemistry and time. Somewhere beneath them, subducted slabs are melting again, creating new magma that will rise cool and one day become the next range of peaks. The pulse never stops. You close your eyes and let the warmth of the stone seep into your skin. The earth shifts once more, too slowly for anyone to feel. And yet, everything moves. The crust, the mantle, the atmosphere, all participating in one slow, patient heartbeat that has kept this world alive since it began. You're lying in the pulse of creation, and for the first time, you notice it's the same rhythm as your own. You stay still for a long time, feeling the pulse beneath you fade into quiet. When you open your eyes again, the mountain light has softened, and the ground smells faintly of minerals and moss. You begin to notice something you hadn't before. Tiny patches of color clinging to the rock, rusty reds, sooty blacks, pale greens spreading like watercolor stains. Life, in its most secret form, is painting the stone. Bacteria, algae, fungi, microbes so small you could fit billions of them into a thimble. They live not in defiance of the rock, but in cooperation with it. They eat metal ions, breathe chemical fumes, and build delicate mineral coatings as waste. What you're looking at is the world's slowest collaboration, life and geochemistry, co-authoring a planet one molecule at a time. You lean closer and trace the pattern of color. That red hue, probably iron-oxidizing bacteria, turning soluble iron into rust to harvest energy. The black film manganese oxidizers, tiny chemists using the same principles that power batteries. And that faint green sheen cyanobacteria, ancient sunlight harvesters, still busy weaving oxygen into the atmosphere they invented billions of years ago. Scientists still argue whether life began in deep-sea vents or shallow tidal pools. But either way, its first meals were geochemical. Microbes learned to breathe minerals long before oxygen existed, trading electrons between iron, sulfur, and carbon compounds. That's the foundation of biogeochemistry, the branch of science that blurs the line between biology and stone. You imagine descending into one of those hydrothermal vents again. hot water jets from fissures rich in hydrogen sulfide. To you it smells toxic. To microbes it smells like dinner. They use the chemical gradient hot meets, cold acidic meets, alkaline to power metabolism. Entire ecosystems thrive there without sunlight. Giant tube worms, ghostly shrimp, pale crabs, all fed indirectly by these invisible geochemical transactions. Closer to the surface, the same principle continues. In soils, microbes break down organic matter, releasing carbon dioxide that reacts with minerals, forming new clays and carbonates. In caves, bacteria coax calcium to crystallize. In deserts, thin films of cyanobacteria stabilize dunes, turning loose sand into living crust. Even the air carries spores that colonize bare volcanic rock, beginning the slow process of turning sterile lava into fertile soil. It's easy to forget that you're breathing microbial exhaust right now. The oxygen filling your lungs is the byproduct of cyanobacteria that began their quiet work more than 3 billion years ago. Back then, Earth's skies were orange with methane, the seas green with dissolved iron. As microbes released oxygen, it reacted with that iron forming rust that sank to the seafloor. Those banded iron formations you see in museums, striped red and gray, are ancient records of life's first pollution. Here's your quirky fact: in certain wetlands, iron-reducing bacteria can form literal electrical networks underground. They pass electrons along filaments, creating microscopic power grids that span centimeters, sometimes meters. You could call it a bacterial internet connecting one pocket of mud to another through pure chemistry. Life hasn't just adapted to Earth's chemistry, it's rewritten it. The composition of the atmosphere, the color of the oceans, even the minerals in the crust have been shaped by living processes. Before photosynthesis, there were only a few hundred known minerals. After oxygen flooded the planet, that number skyrocketed to thousands. The rocks themselves evolved because microbes decided to exhale differently. Scientists still debate just how far this partnership goes. Some argue that the boundary between geology and biology barely exists, that the planet itself behaves like a single self-regulating organism. Others dismiss that as poetic exaggeration. But as you run your hand over the lichen-covered stone, feeling the roughness soften under a living film, it's hard not to believe the Earth is alive in its own slow way. You picture tiny microbial communities inside the crust, kilometers below your feet, surviving on hydrogen and iron. These deep life ecosystems outnumber all surface biomass combined. They don't need sunlight or oxygen, just the faint trickle of geochemical energy seeping from rock to water. Down there, time moves differently. Generations pass without motion. Chemistry is enough. You take a slow breath and feel a strange comfort in that thought. Life doesn't have to be loud or fast to matter. Sometimes it's just a gentle rearranging of electrons happening unseen, yet keeping the planet balanced. The rock you stand on is not a stage for life, it's part of the performance. The moss beneath your fingertips glows faintly under the afternoon light. The rock once bare now hums with quiet photosynthesis. You realize that the boundary between you and the world is thinner than you thought. The calcium in your bones came from ancient oceans. The iron in your blood once rusted in Precambrian seas. The carbon in your breath was mined from stone by microbes who've never stopped working. You sit back and watch a bead of moisture slide across the surface, carrying dust, spores, and ions. The film it leaves behind will dry react and become part of the mineral again. The cycle repeats endlessly, gracefully. Living geochemistry, you think, isn't a metaphor. It's the truth. The world is one vast cell rock for structure water, for cytoplasm atmosphere, for breath. You're inside it, a single molecule in a planetary metabolism that's been running for 4 billion years without ever missing a beat. You exhale and a part of you joins the cycle. A few carbon atoms returning to the air, ready to begin again somewhere else. Night has fallen again. The mountains behind you fade into silhouettes, and the wind has gone still. You sit alone on a quiet plain, the world hushed, except for the faint hum that seems to rise from deep within the ground, a sound not heard but felt. It's the vibration of atoms, the slow murmur of a planet older than memory. Beneath you lies a single grain of mineral smaller than sand, older than the moon. It has survived everything. Fire, flood, impact, burial, resurrection. It hums faintly, not with noise, but with energy. Each atom within it quivers ever so slightly, bound by forces older than stars. You close your eyes and try to imagine time from the perspective of that grain. For the mineral, 1,000,000 years is just a single blink. It remembers magma, remembers oceans, remembers being part of a mountain, and then dust again. Its atoms never stop moving, even in silence. At the atomic scale, stillness doesn't exist, only slower motion, only smaller vibrations. Those tiny oscillations are what make heat, what make sound, what make existence itself possible. You picture the whole planet shimmering with that same motion, an invisible orchestra of atoms vibrating in harmony. Silicates, oxides, metals, all playing their parts in a song so slow that only the universe itself can keep time. The Earth hums faintly but constantly, a planetary lullaby you can only feel when everything else is quiet. Scientists call it the microseismic hum. Tiny waves of vibration caused by ocean tides and wind passing through the crust even when the world seems utterly still. It's measurable, real, a heartbeat of stone. The same vibrations move through you, through your bones, through the iron in your blood and the calcium in your teeth. You're not separate from the hum. You're part of its echo. You think of everything you've traveled through tonight. The molten birth of rocks, the colors of the crust, the breathing of stones, the secret oceans hidden in minerals, the falling sand, the sleeping volcanoes, the scent of petrichor, the whispering caves, the starlit meteorites, the salt plains, the living clays, the gold veins, the trembling plates, the breathing microbes. Each piece has been moving toward this moment, the stillness after understanding. Geochemistry isn't just about elements or reactions. It's about connection. Every atom inside you has shared space with mountains and oceans, with volcanoes and meteorites, with creatures long extinct. You are geology rearranged into consciousness stone that learned how to dream. You look up. The stars don't seem so distant anymore. Somewhere, another world hums like this one, its own minerals vibrating, its own chemistry whispering possibilities. Maybe far away, another traveler sits quietly listening to their planet's song, feeling the same slow comfort. The ground beneath you cools. The air settles into calm. The hum grows softer, fading into the edge of perception, like a heartbeat slowing as sleep takes over. You lie back feeling the weight of gravity, the warmth of the ground, the infinite patience of the world. Time loosens its grip. The boundaries between your breath and the planets dissolve. You are no longer an observer. You're part of the rhythm, one more mineral vibrating gently in the dark. The earth exhales. So do you. Everything settles into equilibrium. The chemistry continues without you needing to notice, carrying your atoms forward into tomorrow and the tomorrow after that. Nothing lost, nothing wasted, only rearranged. The hum fades into silence, or maybe you fade into it. Either way, the world keeps turning quietly, faithfully. And somewhere deep below, the oldest mineral in the world glows faintly in the dark, its atomic heart still trembling with the softest sound imaginable. Morning light returns, but the world feels different now. Softer, wiser, slower. You're no longer tracing only what's beneath the earth. You're following what rises from it, the air itself. Because even the sky, that infinite blue, is geology in disguise, a thin, invisible crust of gas born from stone. You take a slow breath. It's strange to think that every inhale, every sigh, is a chemical letter written by the planet long ago. The oxygen you pull into your lungs was exhaled by rocks and bacteria, oceans and volcanoes. The nitrogen that makes up most of the air was forged in magma chambers and released during ancient eruptions. Even the argon drifting silently through your breath is the decay product of potassium and minerals, a faint echo of the planet's radioactive heart. You tilt your head back and imagine the first sky-billowing clouds of steam and sulfur-black rain falling into molten seas. Early Earth's atmosphere wasn't gentle or blue. It was thick orange and heavy with carbon dioxide, methane, and ammonia. The sun shone dimmer then, but greenhouse gases trapped enough warmth to keep the oceans from freezing. Chemistry was doing its best to balance chaos. Then came the great oxidation, when microbes filled the world with oxygen for the first time. You might picture it as a sudden miracle, but it wasn't. It was slow poison oxygen, corroded iron, bleached rocks, and nearly wiped out the anaerobic life that had thrived before. For the planet, it was a crisis of chemistry. For us, it was destiny. You can still see the evidence of that ancient breath in banded iron formations, layered red and gray rocks that form when dissolved iron rusted and sank to the ocean floor. Each layer marks a pulse of oxygen production, a heartbeat of microbial ambition. That oxygen didn't just change biology, it changed minerals, oceans, and even weather. Without it, no blue sky, no fire, no humans pondering bedtime geochemistry. Scientists still argue about what kept that new oxygen from destroying everything. Some say volcanic gases buffered it. Others point to clay minerals that absorbed the excess. Either way, geology and biology formed an uneasy truce, a planetary co-op where rocks exhaled and microbes edited the atmosphere. You glance upward again. The sky looks calm, but it's in constant reaction. Sunlight breaks apart molecules, forming ozone that shields life from ultraviolet radiation. Rain dissolves carbon dioxide, pulling it back to the ground to feed minerals. Lightning strikes, turning nitrogen into compounds that fall as fertilizer. The entire atmosphere is a living chemistry set endlessly looping between gas and rock. Every thunderstorm, every gentle breeze, every snowflake falling in silence. It's all the planet's breath mixing with temperature and pressure. Even clouds, delicate as dreams or chemical artifacts, water vapor condensing around dust, pollen, or salt crystals. The smell before a storm, that faint metallic promise, is ozone produced by electrical discharge. The low rumble of thunder, expanding air, heated by chemistry gone briefly wild. And here's your quirky tidbit. Scientists have found that cosmic rays striking the upper atmosphere can create tiny bursts of radioactivity, turning nitrogen into carbon-14. That's the isotope archaeologists use to date fossils and artifacts. In a way, every human history is measured by the same sky chemistry that began billions of years ago. You close your eyes and listen to the wind. The air moves in layers, warm currents, rising, cool ones, falling. It feels gentle, but the forces at play are vast. Air molecules bump into each other trillions of times per second, trading energy and motion, turning sunlight into pressure into storms. It's fluid chaos, rendered invisible. If you could see it, the sky would look like a slow ocean. The boundary between Earth and space isn't sharp, it's gradual. The atmosphere thins, but never truly ends. Molecules drift upward, lost to the solar wind, while others rain down from meteorites and comet dust. Even the air is recycled, a balance between gain and lost, breathing and forgetting. You think about the carbon dioxide rising from your last breath. It floats upward, spreads wide, and begins a journey of unimaginable patience. Some of it will dissolve into the ocean, where it will react with calcium to form carbonate shells. Some will be absorbed by a leaf, turned into sugar, then eaten by an animal. A tiny fraction might fall as rain react with silicate rocks and lock itself into the crust for millions of years. Every molecule of carbon lives multiple lives. Scientists still debate how stable the atmosphere truly is. Could it shift again dramatically as it did in the distant past? Could another chemical revolution sweep through the skies? Maybe. But for now, the system holds a precarious equilibrium, maintained by volcanoes, oceans, and forests working in slow harmony. You open your hand and feel the invisible weight of the air pressing down about 1 kilogram per square centimeter. It's gentle, constant, reassuring. The atmosphere is both fragile and immense, a thin veil that makes all life possible. Without it, Earth would be a silent rock, lifeless and colorless, a forgotten marble in the dark. The wind moves again, brushing your skin. You can almost hear the planet breathing, molecules rising and falling like tides. Somewhere a cloud forms, somewhere else rain falls. Each drop completes a chemical promise made long before you arrived. You inhale deeply, letting the air fill your lungs, and think about how long this single breath has traveled, from volcanoes, from microbes, from ancient oceans, and meteor impacts. You're not just breathing air, you're breathing time. And when you exhale, your carbon joins the great atmospheric conversation once more. Another sentence in the planet's endless poem of chemistry. The world grows quiet again. But this time, silence feels larger, almost cosmic. You've traveled from the depths of magma to the thin skin of air, and now your mind drifts outward into the dark. Because if geochemistry tells one story clearly, it's this: Earth is not alone in its chemistry. The same reactions that shape our world are written across the solar system, carved into moons, comets, and planets that glow faintly in distant sunlight. You imagine standing on Mars, brushing red dust from your boots. That dust is iron oxide, the same mineral that turns Earth's deserts red and your blood crimson. The entire planet is essentially rust, a frozen reminder of a time when water flowed freely and chemistry danced in liquid form. In ancient riverbeds, scientists have found clay minerals and sulfates, proof that water once whispered across its surface. Mars, too, once breathed. Then there's Venus, Earth's evil twin. Nearly the same size, nearly the same composition, but its atmosphere is a nightmare of carbon dioxide and sulfuric acid. Its surface bakes at nearly 900 degrees Fahrenheit, hot enough to melt lead. Yet even there, chemistry doesn't stop. The clouds shimmer with microscopic crystals of sulfur and iron. Lightning flashes in dense haze. Some scientists even suspect microbial chemistry might linger high in its atmosphere, surviving on the faintest traces of sunlight. And farther still beyond the asteroid belt, Jupiter's moon Europa sleeps beneath a shell of ice. Cracks scar its surface, leaking plumes of salty water into space. Instruments have detected sodium chloride, the same kind of salt found in Earth's oceans. Beneath that frozen crust lies a global sea, warmed by tidal forces and brimming with potential. The idea that alien oceans might share our planet's mineral recipe feels both strange and inevitable. Scientists still debate whether life needs Earth-like conditions or if chemistry can find other paths: methane lakes on Titan ammonia seas, on exoplanets, silicate atmospheres, on super-Earths. The periodic table doesn't discriminate. It's happy to build worlds anywhere, given a little patience. You look back toward home from this imaginary distance. Earth glows softly blue, not because of magic, but because of light, scattering through oxygen and nitrogen. The continents are just mineral scabs, the oceans vast dissolving vats, the clouds ephemeral chemistry. The entire planet is a reaction in progress, and you're part of it, a mobile geochemical instrument with thoughts and curiosity. Closer to the sun, tiny Mercury carries evidence of volatile elements trapped in its crust. Farther out, Saturn's moon Enceladus sprays plumes of water and silica into space. In those jets, NASA's Cassini spacecraft found organic molecules, carbon chains complex enough to hint at the beginnings of life. Across billions of miles, and the same chemistry repeats itself like a melody that refuses to end. Here's your quirky tidbit: diamonds don't just belong to Earth. They've been found inside meteorites, likely formed under shock pressure from cosmic collisions. Some are microscopic, others large enough to shimmer visibly. The universe apparently enjoys a bit of glamour too. You drift farther still beyond the planets, where comets glide through the dark. Each one is a frozen archive of the solar system's youth, ice dust carbon compounds, all preserved for billions of years. When sunlight warms them, they release vapor trails that shimmer like silver hair in space. Those tails are pure chemistry, sublimation, photolysis, ionization. All simple reactions performing a cosmic ballet. And then beyond even that, you find interstellar dust, tiny grains of silicates and carbon coated with ices of ammonia, methane, and water. These grains float between stars for eons, until gravity pulls them into new suns, new worlds, new stories. Every generation of stars builds the next set of elements, each explosion adding more ingredients to the cosmic pantry. Scientists still argue where the boundary between chemistry and life truly lies. Is life merely a set of reactions complex enough to maintain itself, or does it require intention? The universe offers no answer, only patterns. Reactions repeat, atoms rearrange. Somewhere, perhaps on another world, a listener like you might be staring at their sky, thinking the same thought, that chemistry is not cold, but deeply intimate. You realize that everything from the water in your veins to the calcium in your bones was assembled from stardust. Supernovae scattered iron, magnesium, and silicon across light years. Gravity gathered them into a planet. The Earth forged them into mountains. And now, for a brief moment, they form you. When your atoms return to the ground, they'll rejoin the same endless story. You close your eyes and picture it, the entire universe breathing. Stars inhale hydrogen, exhale heavier elements. Planets inhale dust, exhale light. Even you inhale air and exhale the same carbon dioxide that once belonged to comets. It's all one rhythm, one infinite exchange of atoms. The night sky above you sparkles not with distance, but with connection. Each point of light is a furnace of chemistry, making the ingredients for future worlds. You realize geochemistry isn't just Earth's story. It's the universe's love language written in elements, translated through time. You take a final deep breath. Somewhere, hydrogen is fusing. Carbon is crystallizing, ice is sublimating, and gravity is sculpting the next generation of worlds. It's all happening quietly, endlessly. The universe hums, the same low, steady vibration you felt deep beneath your feet, now stretching across galaxies. It's not loud, not dramatic, just patient. A single eternal chemical chord that has been ringing since the first star ignited. You smile into the darkness, knowing that you're part of that sound. And as you drift towards sleep, you can almost hear it fade into the distance. The song of stone, water, air, and fire echoing forever through the quiet. You let your mind slow. Thoughts soften into quiet ripples. The world feels heavy in the best possible way, solid, grounded, certain. The air moves over your skin with the gentleness of deep time. You imagine yourself sinking into the Earth's rhythm, your heartbeat aligning with its slow vibration. The pulse of molten rock, the drift of continents, the silent rain of dust, each movement steady and kind. Everything happening exactly as it should. Nothing rushing, nothing forced. You think about how the same atoms that once drifted through the cosmos now rest in your bones. You're not separate from this planet. You're one of its experiments in awareness. The stones, the water, the air, all of them speaking the same quiet language of chemistry. Even now, as night deepens, reactions continue, crystals forming under mountains, ions shifting through clay, microbes breathing metals in darkness. The planet doesn't sleep, but it dreams, and tonight, you're part of that dream. The hum beneath you fades into stillness. You feel weightless, as though the boundaries of your body have dissolved into the soil. The warmth of the planet wraps around you like a blanket. The stars above flicker in slow time, patient and endless. You take one last deep breath. The air is cool, mineral-rich grounding. You let it fill your lungs and drift out again, leaving only calm behind. The earth whispers, "Rest now." You've wandered far enough for one night. And as you close your eyes, the last thing you hear is that faint, eternal vibration, the quiet heartbeat of the world, steady and kind, carrying you into sleep.